Hello. Is it working? Is the microphone functioning? In fact, the title of my talk changed somewhat since the time I gave it to the organizers, and it became somewhat longer. It's now called From Motives to Motivic Homotopy Types. And for the first half of my talk, I'll be speaking about sort of the history of motives, because it was my impression that the talks on this conference, which were about the development of one subject or another, were the ones most enjoyable. So I counted 4 periods in the development of what we now call the theory of motives. And of course, I am in fact somewhat biased. I omit certain things because I want, basically I omit things which I don't know. So the beginning of the whole thing was the study in the 60s and the 70s of individual, particular cohomology series or cohomological invariants of algebraic varieties. And there were many, of course, but if one puts certain restrictions, then it turns out that one can list all of them. So I claim that this is the list of all cohomology series on categories of algebraic varieties. This is okay. This is how I want it to be. Which satisfy certain conditions. Namely, series of this list are defined for all or almost all fields. And second, this series take values in the category of abelian groups without any additional structures. So if we consider only series satisfying these 2 conditions, then these are the only ones I know.
What about the crystalline?
Crystalline takes values I don't quite understand where. And it's only defined in characteristic P. So, and most importantly, I don't quite understand where it takes values. If there are modules over something. Now, between this series, there is a bunch of natural transformations. Again, all of them can be listed. And the picture looks as follows. It's not very informative. Again, the funny thing is, I don't know of any others. So this whole messy picture was appeared again in the 60s and the 70s, maybe late 70s, maybe with the exception of the Ital-K theory, which came by a little bit later. So there was a first attempt to put some order in this picture, which was made in the end of the 60s by Grothendieck, and which was mostly unsuccessful. In fact, Grothendieck had only these 2 gadgets to work with. The rest of them were basically non-existent at that time.
What's the meaning of arrow?
An arrow is a natural transformation. It's a collection of homomorphisms going from abelian groups of one theory to abelian groups of another theory. So one outcome of this Grothendieck's attempt was the formulation of a bunch of conjectures, which we now call the Grothendieck standard conjectures. And in fact, this was also the major outcome of this whole period. The main thing which happened was that 3 blocks of conjectures were formulated, some of them a little later, but I still put them into this period. And these 3 blocks of conjectures, of course, came out to be just by computation of examples. They can all be organized. Yes, I will go into details in a moment. So let me maybe even put it here. Interestingly enough, they can be pretty well organized, because all these conjectures are, in fact, conjectures about certain properties of one or another of these natural transformations. So these are never conjectures about a theory. It's a conjecture about the relations between 2 theories. So if we look at the Grothendieck standard conjectures, and of course I took away the part of them which deals with the Hodge structures because it doesn't fit into the picture. It's a theory which takes values, doesn't take value in the category of abelian groups, but rather in something much more structured. Then we basically see that what is left are 2 things. There is the hard Lefschetz, and more or less equivalent to it, statement about homological equivalence of cycles being equal to the numerical equivalence of cycles. Both of these conjectural statements concern the behavior of the natural transformation from Chow groups to L-adic cohomology for smooth projective varieties in the case of rational coefficients. Well, QL as opposed to ZL. It should be noted that no progress on these conjectures was made since they appeared. The next bunch of conjectures, in fact, 2 of them came much later, and I didn't have time to ask Sasha exactly when. So when did vanishing appear? Aha, so it's early 80s. It fits even better into, into my picture. So as far as I understand the story of the vanishing conjecture, it was originally a statement about the behavior of the characteristic classes going from Quillen-Thomason, meaning just ordinary algebraic K-theory, and taking values in the L-adic cohomology. Again, only smooth varieties are considered, which is not important. No, it is important. Only smooth varieties are considered, and only rational coefficients are considered. So the statement is the following. I have to introduce an additional structure on the Quillen-Thomason K-theory to formulate it, which is the action of the Adams operations. And the statement says that these characteristic classes, or regulator maps, whatever we call them, it's the same, in this particular case, the same thing. They're injective on certain pieces of the filtration defined by action of Adams operations. In fact, in most cases, this just means that the corresponding pieces of gamma filtration are 0 because the corresponding L-adic cohomology groups have negative indices and therefore are 0. Now that's where vanishing comes from. And the third block, so we had 3 blocks, and the third block is a bunch of conjectures which all talk about finite coefficients or torsion phenomena and about different possible homomorphisms, different possible natural transformations. So the original one was Milner's conjecture. It was something like mid-70s, I guess. 1975, maybe it was published. And this talks about natural sequence of maps from Milnor's K-theory to the graded Wittring of quadratic forms, and then going to adic, in this particular case, just with Z2 coefficients cohomology. There was generalization of this thing, which is now called Bloch-Keira conjecture, which talks about the map from Milnor's K-theory to L-adic cohomology for L greater than 2 and not equal to the characteristic of the field. And there was also something called the Quillen-Lichtenbaum conjecture, which talks about the map going from the Quillen-Thomason K-theory. So Quillen-Thomason K-theory is just what we are used to call algebraic K-theory, to the Ital K-theory, which was introduced by Friedlander, I believe. So these conjectures, which are very closely related to each other, it was only recently completely understood how, form the third block. So these three blocks of conjectures is what we inherited from this first period of development. And these are our beacons in the sense that what we want to do is to prove all of them. Of course, on the way, developing beautiful theory of all cohomology theories on the category of algebraic varieties, otherwise makes no sense. So let's go back to the story. So sometime in probably early 80s, again, I'm not very good with numbers, with dates. There began, or at least the papers began to appear, which properly belong to a new period. And this new period, the two main names, maybe I should say the names. So the first period, of course, the main name is Grothendieck, but then it's also Deligne, I guess, though it's more, he more belongs to the second. Milnor, Quillen. These are the names which come to my mind when I'm thinking about the first period. Partly maybe Friedlander, because of the Ital K-theory. Now the second period, the main names become, in my understanding, Berlinson and Lichtenbaum. So behind this there is probably Deligne, but I don't know if he ever published anything about this. So the main innovation is the idea of motivic cohomology. This motivic cohomology is a new theory. In fact, as it happens, let's see what I wrote here. There were two axiomatics for motivic cohomology which were suggested at the beginning of this period. One was suggested by Berlinson and another one by Lichtenbaum. They were very similar, but somewhat differed. And as we now understand very well, they do in fact describe two different motivic cohomology theories, which come to be together with a natural transformation going from the Berlinson to the Lichtenbaum. So something completely new which happened is that both of these theories are bigraded. All of the previous theories, the theories of the first period, they have only one index. These theories are bigraded. Besides, it's completely independent. They're bigraded. Hodge theory doesn't fit in because it's only in characteristic 0.
So what he means is the bigrading of a complex manifold, is it related to this bigrading?
No.
Okay.
Well, I mean, not in any obvious way. Parallel to this, there was a second attempt at systematization. Namely, there was the idea of mixed motives, which was an extension of, more or less direct extension of the Grothendieck's idea of motives. But then there was also the idea of motivic sheaves, which, as far as I understand, again, belongs to Balançon, which was completely new as far as the systematization of these ideas go. So as of today, this approach remains conjectural. That will take too much time. But basically, that's the idea that motives should properly be considered not only for varieties over a field, but also for families of varieties over an arbitrary base. And that this vague statement can be made into a certain more or less precise picture.
More innovation about it. What you said, there is no vanity. There's something more to that. Yeah, this is canonical operation.
Well, at Grothendieck's time, it was not canonical at all. He would never think of considering motives over a variety. It would make no sense for him whatsoever. And all these functors, which modeled the functors between the categories of sheaves as all different types of direct and inverse images going between motives, that was not in the picture at all, at least not in the published picture. I don't know what he had in his head. It was completely 100% absent. And here, this is the first place where it appeared in a published form. That's all I can.
No, I'm not saying that. There's some power to this idea which is not visible. Yeah, this is great geometry. Always give an object you consider relativized. So but here is something more, apparently, which you didn't say. This idea is something of power which is invisible, what you say.
There is a certain way, well, let me not go into it. There is a certain picture. This would take a completely separate talk. At the very end of mine, I'll draw the picture which we have today, which has something coming from there and something coming from somewhere else. And we'll see. I'll show you the things which do come from there. Yes. So as of today, what we know of this systematization approach is the following. First of all, it's definitely incomplete. It's unable to deal with finite coefficients phenomena. Second of all, it's unable to deal with things like algebraic K-theory, which we now understand are not ordinary cohomology series, but rather generalized cohomology series. And on the third, however, part of our knowledge is that we do expect it to work for ordinary cohomology series and rational coefficients, and this remains to be completely conjectural. And if we could figure this out, that this would be a great progress. So I'm not really going to talk about this attempt of systematization. I consider this is outside of what I'm going to talk about. So with the introduction of this idea of motivic cohomology, the landscape of the series, so we had this picture, and now the landscape has changed. And the picture with motivic cohomology in them looks approximately as follows. It looks more complicated, but it's just because there is much more information on the slide. So first of all, before someone asks, I cut off the wheat ring for my own reasons. I'll later say how it fits into the picture. But it will just mess things up. So what we now have is this 5 series. So these arrows here refer to characteristic classes maps, natural transformations. The dotted arrows going back mean that there should be a spectral sequence starting from this and converging to this, correspondingly starting from this, converging to this. And this whole square completely commutes in all reasonable meanings. And then there is a map going to the L-adic cohomology. So one important thing which happened is that Milner's K-theory and Chow groups sort of disappeared in a sense that they both were discovered by, again, Balanson, I believe, should be just parts of this new bigraded theory. So since now we have two sets of indices, there are much more possibilities to fit different groups in there. And Milner's K-theory is supposed to be the diagonal, and Chow groups are supposed to be the double diagonal. The ordinary étale cohomology with coefficients in the roots of unit turned out to fit into the Lichtenbaum Motivic cohomology theory. So for those who know what I'm talking about, the Lichtenbaum Motivic cohomology is the same as Balanson, but it's in the étale topology. So it's just the étale hypercohomology with coefficients in the Motivic complexes. But it makes a lot of sense to consider them as a separate theory, and this makes the picture much more understandable. So this was the change of landscape. And then there was also corresponding to a change in the structure of conjectures. So we basically have, again, of course, three groups of conjectures. Now all of them can be formulated purely in terms of Motivic cohomology. So the Grothendieck standard conjecture, this is something which I did some years ago, can be reformulated, and well, it's not exactly a reformulation, it's a strengthening. There is a conjecture called the nilpotence conjecture, which I have written somewhere, and if someone is interested, I can show it, which is formulated basically directly in terms of the Chow groups, and it's a statement of something is 0. Nth power of something is 0, which implies the standard conjectures, hard Lefschetz, and this kind of stuff. There is vanishing and rigidity was originally reformulated by Balanson in terms of Motivic cohomology. It was a very natural reformulation, which the vanishing part says that Motivic cohomology with negative first index are 0. And all the finite coefficients conjectures, it was understood how they all follow from one conjecture, which is called the Balanson-Lichtenbaum conjecture, and which looks as follows. So the map going from Balanson, this natural transformation from Balanson cohomology to Lichtenbaum cohomology are isomorphisms when the first index is less or equal than the second. It should be noted that they're very much not isomorphisms when the first index is greater than the second, which is where the whole problem, of course, is. Yes.
How can we, for example, each one on the one of those was the risk topology of this jam, and the color is the same, the
Yes.
generalization.
This is a huge generalization of this statement. And it was well understood how all the three kind of classic standard conjectures on finite coefficients follow from this one, and the relations existing between the series. So in a sense, this is my summary of the second period. Now we have the third period, which is also which is basically also over. And the main achievement of this period was the construction of Motivic cohomology theory and proof of all of their easy properties. So the first successful definition was given by Spencer Bloch. Now we understand very well where it sits among all other definitions. Then there was unpublished definition by Suslin. Then there was definition given by myself, and I don't remember whether independently or together by Eric Friedlander. There was some. I mean, we were all working together. I don't remember how it all happened. In fact, at some point, it became easy to give a definition. It was already clear what's going on. So, of course, the Spencer's is the real breakthrough. And then there was a lot of technical work to prove that all this works as it's supposed to work. It was, I guess, similar to some period of development of topology when people were proving that all different definitions of ordinary cohomologies are the same, and they all satisfy the standard list of properties. So now I would say we're done with it as far as varieties over a field are concerned, and there are some interesting problems left in the case of mixed characteristic, varieties over spec Z. So there is almost everything is clear, but not all. And this is the main point. Today we know that all the definitions of Motivic cohomologies which are supposed to agree. So we do have one, or rather two, Motivic cohomology series. There is no doubt that this is the only one satisfying expected properties. Well, this, so there, we know how to construct two. We know how to construct the Berenson Motivic cohomology and how to construct the Lichtenbaum Motivic cohomology. They conjecture. Didn't I say it? No, they just, yeah, they conjecture. Simultaneously, there was a third attempt on systematization, which we now know as the theory of triangulated categories of motives. There were a bunch of constructions of triangulated categories of motives done by Mark Levine, myself, Hanamura, and maybe someone else. Again, we know that they all agree, and they all give the same category up to certain differences which must be there. For example, one is a bit bigger, one is a bit smaller, meaning one admits infinite dimensional objects and another one doesn't. And this was a very useful thing for this part of development, but then it turned out to be of somewhat limited use for harder things. There is no hard theorem, there is no interesting theorem which would be proven just with the use of the fact that there is a triangulated category of motives. But it did help to systematize things.
So do I understand, like, triangulated category means there's something like ordinary homology can be given by chain complexes, and they have the category of chain complexes have certain properties, like uniform quotients, kernels. Is that what it means to triangulate categories?
Yes, but it's not like a category of complexes themselves, but as a category of complexes, is a homotopy category of complexes, where you don't have kernels and co-kernels anymore, but you have cones. Yeah. And so you have this distinguished triangles, so-called. It's a very...
It's like stable Hall.
Yes, yes. Yes. So canonical examples has a stable homotopy, categories of all sorts, the derived categories of all sorts. And now we are in the fourth period, which it's probably not written here very well. So there are two things which should be distinguished. first thing is it's a very good progress, or it's more like the final progress on the whole block of conjectures relating to finite coefficients. So the picture as it is today looks as follows. So I'm back to the balance on Lichtenbaum conjecture. And here is what we have proven. So it's more or less trivial, or not trivial, but easy for rational coefficients. It is now proved for coefficients localized at 2. So if I invert everything but 2, then it's true, which in particular implies the Milnor conjecture and all this bunch of things with Z2 coefficients. As far as I understand, there is also a part of it which actually talks about ZP coefficients when P equals characteristics. And as far as I understand, this is also proven. So I was far from this part of things. And ideology, I mean, it's in the writing, more or less, for general L. But since it's not written, there still can be things coming up. But it's in this stage for about 2 years now, and nothing bad happened. So this is the first thing about this force period. And it was achieved because, as far as, not only because, but partly because, we have finally succeeded. I think we, huh? You wanted that? Names or? Okay. We finally succeeded in systematization. So I would say that this is done. I really don't know of any. I mean, this is self-contained, in a sense, theory now. I will give it in a rather general form, and just an outline, of course, a very, very brief. So first of all, I want to move from varieties over a field to families of varieties over any scheme S. So this gadget schemes over S, if we want intuitively, these are families of algebraic varieties parameterized by scheme S. So it's algebraic varieties over S, schemes over S. This all doesn't matter in this theory. An important example is, of course, when S is the spectrum of the integers, in which case we get the theory of algebraic varieties over integral numbers. Mixed characteristic case. The picture looks as follows. So for each object there, we have a category. So this beginning is just taken directly from the idea of Motivic sheaves. We have a category which one can think of as some analog of in this ideology of Motivic sheaves, it was expected that for any category, for any variety, there will be an abelian category of so-called mixed Motivic sheaves over it. And then, of course, having an abelian category, I can take the derived category. And in fact, all the computations happened in the derived category, but only their properties indicate that this is a derived category of something abelian. So this gadget over here is our modern replacement for the derived category of the abelian category of Motivic sheaves over X. We know that it is not in a reasonable way a derived category of anything. So this category has two commuting autoequivalences, which is, I don't know if it's readable at all, it's denoted by sigma with the index S and sigma with the index T. Give two suspensions, sort of, in this theory.
That's a bigrading?
Yes, well, it's not a bigrading of a category, but it's a bigrading of all the groups, which can be constructed in this theory, which is written right over here. Now, for every morphism, between algebraic varieties, there are 4 functors, as one would expect in the category of sheaves. So there are, every morphism meaning morphism of finite type, and the schemes were of finite type, I'm sorry. And all these functors satisfy the usual properties of the 4 functors in the theory of sheaves. For example, the lower star and lower factorial, lower shriek are the same for proper morphisms. And upper star and upper shriek are closely related for smooth morphisms. Using these 4 functors and the 2 autoequivalences, we can associate to any object of the category sitting over the base 4 types of theories, or 4 theories rather, which are obtained using these formulas. There is also a distinguished object 1, which, yeah, it's written here. So this gadget is called cohomology. This is called cohomology with compact support. This is called homology, and this is called the Borel-Moore homology. They all satisfy the standard functoriality conditions. This is contravariantly functorial for all. This is covariantly, contravariantly for proper, and covariantly, almost covariantly for smooth, or let's say covariantly for étale. This is covariant for all, and this is covariant for proper and contravariant for étale. This is in every object, any object of F. For any object, we get 4 series.
Any object you have a homology group. So in the case one makes spectrum out of the subsequent one.
Well, this is already a spectrum. This is an object of this stable homotopy category sitting over the base.
So it's a spectrum. Every object is stable through it.
Yes, there is this SHOT. I don't know why it's.
Stable now.
This is a stable homotopy category. For every object, we get this 4 series.
Can you say what an element, an object in S hot is, or map is?
What a map is, it's hard to see. Of course, it's very hard to compute. It's just like, what is a map in the ordinary stable homotopy theory? And this is not very clear.
Class of maps.
Well, between what? If you take some arbitrary spectra, if you take between some arbitrary non-fibrant spectra, then it's very hard to say what it is. So the objects of this category are spectra. These are sequences of, there is a certain sequence of things which have to be said. First of all, there is something called a space over S, which is basically a sheaf of sets on the category of smooth schemes over S in a certain topology. This, in particular, scheme defines a representable sheaf, and this is embedding of schemes into smooth schemes into the spaces. Now, this category of spaces has all limits and co-limits because it's a category of sheaves. And what an object in this S-hot is, it's a spectrum. It's a sequence of these spaces together with maps from the suspension of the n's to n plus first. And the suspension is given as a smash product, which is easily defined for this spaces with the projective line. Now, this whole gadget, just this collection of the spectra, is in itself a category which has all limits and co-limits. And one can define a notion of a weak equivalence, which turns it into a equivalence closed model category. And this is the homotopy category of this equivalence closed model category. So objects are the sequences of spaces. Now, for each of the classical theories, where is my list of classical theories? There is an object in the stable homotopy category which generates this theory in the sense that the associated cohomology theory is the theory we're talking about. All the natural transformations written on another slide corresponds to maps between the corresponding objects. This also brings in some other kind of order because, for example, for Quillen-Thomason K-theory, there are two different incarnations. There is a K-theory of vector bundles, and there is a K-theory of coherent sheaves, which are somewhat different. Now we understand that the K-theory of vector bundles is a cohomology theory, and the K-theory of coherent sheaves is the Borel-Moore homology theory, which coincide for smooth varieties. And there are two others which are not really studied very well. The same thing happens with Motivic cohomology. High Chow groups are in fact not Motivic cohomology, but rather Motivic Borel-Moore homology. Now, let me try to lift this up and use the blackboard. Will I be able to do it myself? Aha, so I was very good.
No, opposite direction.
Correct.
That's what I want. No, it's doing right. Now, where we are now, this systematization is almost completed. There are natural questions which we don't know how to answer in the case of mixed characteristic, like, for example, purity. So this first question which I want to formulate, it is, if I have a regular embedding, then for any object over X, there is a canonical map, a canonical morphism going from the I upper factorial of E, I don't remember the direction of the arrow, unfortunately, to the I upper star of E, smashed with the Tom spectrum of the normal bundle. There is such a map. It either goes in this direction or in that. I don't remember. We expect this to be an isomorphism. This is the purity conjecture. It would imply, among other things, the existence of the Gersten resolution in algebraic K-theory, something in mixed characteristics, something which is still open. Yeah. In fact, as far as conjectures concerning general functoriality, we're talking about this kind of conjectures. This is the only one which remains, as far as I understand. In topology, people are not used to considering families, not in the stable homotopy theory. Now, maybe what I should mention is that all things live over a field, then it is known to be true. This is only a problem in mixed characteristic because we don't know how to turn it around, as usual. So this is one and only conjecture which I know about the general picture. Now, there is a bunch of things concerning the relations between different distinguished objects in these categories. As I mentioned, for each of the classical theories, there is an object. So there is an object, for example, H with the index C, which is called the Eilenberg-MacLane spectrum, which represents Bailinsson's Motivic cohomology in the sense written there. there is an object called BGL, which represents Quillen-Thomason K-theory. There is an object called MGL, which represents algebraic cobordism, something which is not one of the classical theories, but which is very important anyway. There is, of course, an object 1, which is a distinguished object, the unit of the tensor structure, which represents algebraic stable homotopy and cohomotopy groups. There are conjectures concerning the relations between these objects, which again express something rather classical. So one thing, there is the Atiyah-Hirzebruch spectral sequence. I put it in quotes. It stops being a spectral sequence. It becomes a Postnikov tower, which expresses BGL in terms of the Allenberg-MacLane spectrum. It can be easily written exactly what it should be, and the question is whether or not the gadgets which appear there are in fact distinguished triangles. It's partly answered over a field.
Whether or not they're what?
Whether or not there are distinguished triangles, which means whether or not there are cofibration sequences. There are certain sequences, and the question is whether or not there are cofibration sequences. There is a similar question constructing. Yes, the notion of a Postnikov system just requires this triangulated structure. For any triangulated category, there is a notion of a Postnikov system. Of a Postnikov.
What is the question then?
Well, the question is to compute its stages,
Oh,
if you wish.
compute it.
Yes.
See what it's not
Yes.
trivial.
Yes. Well, it's not exactly that simple, because the Postnikov, I mean, there are many Postnikov towers one can produce for an object. Not necessarily the classic one. And here the picture is not, it is now clear, but it's not what one would immediately expect it to be. So there is an analogous problem computing the Atiyah-Hirzebruch spectral sequence for algebraic cobordisms. It might actually be, from the general point of view, somewhat easier. The third thing is to understand the dependence between these two objects. And this is very interesting. This is where some progress was recently made. So this object represents Motivic cohomology. This is the Allenberg-MacLane spectrum. Ordinary cohomology is the Motivic cohomology. And this is the unit of the tensor structure. So this is the sphere spectrum. And it represents the stable homotopy and cohomotopy groups. Of course, in classical homotopy theories, there is the Adams spectral sequence, which is easily shown to converge. Also, there is a nice description, internal description of this spectrum in terms of the stable category. This is what one gets from the sphere spectrum by killing up all the positive homotopy groups. And this is the meaning of it. There is no other internal meaning for this gadget. So here we have a group of...
Say, the HZ is the free abelian object generated by the one.
Well, in this setting, it turns out to be wrong, simply.
Yeah, but I mean, that's another way. Okay, could be-
Well, it's not a way to say it in terms of the homotopy category. You have to go back up to spectra. It makes no sense to talk about the free abelian group objects generated by stable homotopy type.
Makes sense poetically.
Hmm?
Makes sense poetically.
Poetically.
Yeah.
But poetically, it's here wrong.
Okay.
So,
Well,
no.
makes sense.
Yes, you're absolutely right. And these were the first attempts at how to do things. Let's try to see that this is this Quillen, well, Quillen at least wrote it down, that homology is obtained by abelianization from stable homotopy groups. This is not the case. There is another picture. We now know, I'm sure we know what happens, in fact. And what happens is the following. This HZ, there is this, if I consider, I'll be done in a couple of minutes. If I consider the fiber of this map, and I desuspend it, then this is supposed to be, should I say, localization sequence with respect to objects divisible by the Tate object. This probably won't say anything to anybody except for those who know what I'm talking about. Anyway, there is a certain explicit conjecture about what this guy means, what it is here for. And this conjecture implies immediately a bunch of things about the behavior, of course, of Atiyah-Hirzebruch spectral sequences, because to talk about them, we should understand what this thing is about. As you said, the ordinary Postnikov tower is obtained by taking separate homotopy groups. So it's completely dependent on the fact that the Eilenberg-MacLane spectrum has only one homotopy group. Here, this is wrong. It has plenty of homotopy groups. And so this doesn't work, and it took us a long time to understand what is going on. So there is a bunch of conjectures here relating. The third group is about the relationship between the unit and the Eilenberg-MacLane spectrum. All of them are doable. I mean conjectures, things which seems to be pretty well understood but have to be worked out. Now the last thing which I want to say, this third gadget implies if everything works as it's supposed to work, it should be true that the following holds. If the square root of -1 belongs to the field, this is a necessary condition, then the stable homotopy groups with rational coefficients are the same as Motivic cohomology. Of course, in topology, it always holds. Stable homotopy groups are always the same as homology. But here, it's known not to be true in general.
With Q coefficients or something?
Yes, the tensor Q here. Yes. It's known that if I take K to be R, this is not true, even with rational coefficients. There is some infinite phenomena which produces non-torsion elements. But it is expected that if we have a square root of -1, then this is true. If this is true, we get a new way of describing Motivic cohomology. Because the stable homotopy groups of spheres have natural representation as a colimit of unstable homotopy groups of spheres. So we conclude that Motivic cohomology can be represented in a new way, completely new. It's completely unclear that they can be represented in this manner, which I hope may produce a first, well, a non-trivial but tractable weakening of the vanishing conjecture. A vanishing conjecture says that these groups are zero in some keys. If I can represent them as a colimit of homotopy groups of spheres, then this becomes a statement of this colimit being zero. And since this colimit is in has a very natural structure, and we know that there are many structures existing there, we can try to approach it geometrically and see if this vanishing actually comes from some properties of unstable homotopy groups of spheres which have geometrical interpretation. That's it. Thank you.